When you have first row transition elements existing as either 2+ or 3+ ions, we've seen that they can form hexa-aqua ions where they're dissolved as various salts, and you know that they give coloured solutions. But if you add sodium hydroxide solution to any of those solutions, you get a precipitate, because the hydroxides of these ions are all insoluble in water. So you need to know that. You need to be able to write equations for the precipitation reaction that takes place, and in some cases you need to learn the colours of the ions, and historically that was a method that was used to identify what metal ion was present, because with the ions in solution we've seen that because of the possibility of different negative ions acting as ligands, you can change the colours of the solutions. So chromium, for example, is sometimes violet in the 3+ state if it's the hexa-aqua ion, but it's sometimes, in fact more commonly, green when it has some negative ions participating as ligands. And so the colour of the aqueous ions is not always a good guide as to what element is present, but if you precipitate out the hydroxide, it has a very specific colour which is always the same. So you sometimes get questions based on identifying what the element is from the colour of the hydroxide. So let's see how that works. So here are the 5 specific cases that you need to know about. So chromium 3+ is the first one, and as we've said, the aqueous ion is, strictly speaking, violet, but is typically green because of the participation of some of the ligands in the complex ion. When you write equations for these precipitation reactions, normally the easiest thing is to revert to just writing it as chromium 3+ aqueous. Don't bother writing in the 6 waters. You can if you want, and then you just have to put them on the other side when they get kicked off and form the chromium hydroxide, but it's just overcomplicating it. So keep it simple, just write chromium 3+ aqueous plus 3 hydroxides forms the chromium 3 hydroxide, and it's literally as simple as that. So you just need as many hydroxides as you need to balance the charge on the metal ion, and then they fall out of solution when they meet and form the hydroxide. So equation wise this is trivial. Don't forget these ionic equations, particularly when all that happens is a precipitation. You should generally make sure you put the state symbols in. But the bit that you've got to put your memory into is remembering the colours. So chromium 3 hydroxide is green, and you need to know that. There is this extra complication about redissolving in excess. We'll talk about that in a minute, but for the moment focus on the fact that you've got to learn that CrOH3 is green. And you can see it's a similar story for all these other ones. So in the earlier video we learnt the colours of the aqueous solutions. So manganese 2+, it's very pale pink, so much so that it looks almost colourless. But when you add the hydroxide ions, you get this light brown precipitate forming of manganese hydroxide, MnOH2. And iron 2+, pale green solution, green precipitate. It's a different shade of green from the chromium 3 hydroxide one, so in real life there's no ambiguity there. You can tell which one it is because it's a different shade of green, but you don't need to worry about that for A-level. Fe3+ has this kind of orange-brown colour. In the old syllabus they used the term foxy red, which I always rather liked, but these days it's a rather more prosaic orange-brown that they go for. And copper 2+ forms this blue precipitate of CuOH2. So more colours to memorise, I'm afraid, but at least the equations are very simple in that case. So If you add lots and lots of sodium hydroxide, for most of these metal ions it doesn't make any difference. Once you've got the precipitate, that's it. But again, for reasons we don't need to go into, chromium 3 hydroxide has this interesting property that if you add more hydroxide to it, the green solid that you get initially will redissolve and give you a dark green solution. So you can see you get this sequence at the bottom. So we got the violet, or remember it could have been green, aqueous ion, green precipitate forms, and then a dark green solution when you add excess sodium hydroxide. So again, you need to know that only chromium 3+ does that, and you also need to know the formula for the dark green ion. So what happens is that you now have 6 hydroxide ions acting as ligands, all packed around the chromium 3+ ion, and that's the dark green solution, CrOH6 3-. When you add aqueous ammonia to the hexa-aqua ions, the story is a little bit more complicated, because ammonia can do two things. The first is that you know that aqueous ammonia is alkaline because of the ability of ammonia to act as a base, take H+ away from a water molecule, and form ammonium ions, which leaves OH- behind and makes the solution alkaline. So, of course, the first thing ammonia can therefore do is cause the hydroxides to precipitate out in the same way that sodium hydroxide would. So you get the same precipitates and therefore the same colours formed when you add ammonia to any of these hexa-aqua ions. But the complication is that ammonia is also a good ligand, so it has a lone pair on that nitrogen, which instead of just here acting as a donor to H+ to form the ammonium ion, could be used to form a dative covalent bond to a metal ion. And the consequence of that is that you get these two processes. With small amounts of ammonia, you get the hydroxide precipitating out, but for some, though not all, transition element ions, those precipitates will redissolve in excess ammonia to form complexes with ammonia as a ligand. And we've already met those, but you just now have this slightly more complicated story that there's this sort of two-stage process. First, you form the hydroxide precipitate, and then when you add excess ammonia, you get the complex ions. So let's just remind you of those. These were the two cases that we learnt where you get ligands containing ammonia. So we've now slightly changed the story and said, right, well, let's assume that we've done the first bit, we've added a small amount of ammonia and caused the hydroxide to precipitate out because of those hydroxide ions present in the alkaline ammonia solution. And then this is looking at what happens when we add excess ammonia and the precipitates redissolve and form those ions that you learnt earlier. So in the case of copper 2+, you get this slightly strange ion in which there are 4 ammonia ligands and 2 waters. So you write the formula out like this, as this sort of copper 2+ and then the list of ligands after it with the 2+ charge. And you remember that's a 2+ ion. And again, they will quite often ask you for equations, and it looks complicated, but it really isn't, because you're just saying, right, here's the copper hydroxide, here are the 4 ammonias and the 2 waters, which are going to end up acting as ligands, so they get incorporated into here, and the hydroxide ions are booted out, so they then just appear as free ions on the right hand side. And the same story with chromium 3+, that initially you get the hydroxide precipitated, so it's green solid, but again, excess ammonia, it will redissolve. And the difference this time is that all 6 of the ligands in the complex ions are ammonias. So you get chromium NH3 3+, and again you have to learn the colour of that solution, which we saw earlier was purple. The other ones, manganese 2+, iron 2+, and iron 3+, they don't redissolve in excess ammonia, so again nothing more that you need to learn there. Okay, so there is a lot of memory work here, because you've got to learn which ions do what, and in particular you've got to learn the colours. So that's a case of practicing and just going through, memorising, do flashcards, whatever works for you. But you get a lot of questions which involve basically identifying what's going on in particular reactions, and they will often use the colours as key clues to that. So you really do need to learn these colours for the A level.